Good afternoon, everyone. We are Team Juran, and we will be presenting a case study entitled Applying SPC to Pharmaceutical Product Manufacturing. As seen in the PPT, we will be following this flow of discussion. First, the case background. Midwest Pharmaceutical Company manufactures syringes with a self-contained single dose of an injectable drug in two stages. As you can see here, this is what the syringe may look like. In the first stage, a sterile liquid drug is filled into a glass syringes and sealed with a rubber stopper. In the second stage, which requires 100% inspection, the cartridge is inserted into plastic syringes and the containment caps are electrically tacked or attached. The cap is tacked at a precisely determined length of the syringe between 4.920 inches to 4.980 inches.
So now, moving on to step 2, the syringes are either scrapped or reworked. It is scrapped or unused if it is less than 4.920 inches, since it may activate the syringe with the pressure on the cartridge stopper. On the other hand, it is reworked if the cap is stacked greater than 4.980 inches, as it may lead to cap loss or cartridge loss in shipment and handling, since it is incomplete.
Given the case, we identified that there are several organizational factors that are in place. First, product quality and safety are crucial in the pharmaceutical industry since the drugs made may impact the lives or health of an individual. Next, they must have proper process to ensure the efficacy and safety of medical products. Lastly, they must adhere to PQS or pharmaceutical quality system. For the external factors, we have researched that pharmaceutical companies would be overseen by regulatory agencies such as the FDA. They also avoid the healthcare policies and take into consideration the economic conditions and healthcare systems.
And now, to visualize it better, we made a flowchart of the process. And since the management noticed that there were more scrap and reworked syringes through the weeks, they called a statistical consultant to help them apply a statistical process control or an SPC.
Okay, so now moving on, we look into the statistical process control that the company conducted. In this slide, we can see the initial 35 consecutive observations taken for the capability study. And they gave us values such as the mean, the standard deviation, the upper limit, lower limit, and the process capability index. So the mean was 4.954 inches, which was close to the nominal aim of 4.950 inches, and the process capability index was 1.03, which is minimally capable and could indeed produce the length desired. In this slide, we show you how we computed for the process capability index. We used the formula that Sir Alvarez previously discussed, which is minimum of the upper limit minus the mean over the 3 sigma, or the mean minus the lower limit over 3 sigma. So we just replaced that with the values that were given in the previous slide, and we came up with the answer of 1.044, which is capable at 3 sigma. So we see here that the process is still in under statistical control, but since the company identified that there was high rework and scrap syringes, they still had to continue with the SPC to find out the root cause of the problem. And to further prove the point that the process is in control, we made a histogram to visualize it. You can see here that it is still within the upper and the lower limits. So we can see here in the charts that the process is already out of statistical control in both charts. You can see here that one point is outside the control limits, but the problem was the operators of this shift did not plot these points. Now in the second shift, they did plot the points and they saw that the process is already out of statistical control in both charts. So you can see here that the problem was that the machine was producing lengths greater than the upper control limit. So what did the second shift of operators do after figuring out that the process was indeed out of statistical control? They called in the maintenance employee to adjust the machine so that it will be back to normal and so that it will be centered again. And after adjustments, the lengths were within control limits. So they took no action. But it was later revealed that it was only a temporary solution and the problem was within the machine itself. As we move on to the case, we realized that the company was facing several issues or problems. They first identified that there was high scrap and rework syringes, so they conducted an SPC. And the results of the SPC was that there was a tacking process variability, but it took them a while for them to realize this because of the operator errors. This shows that the employees had inadequate training and were not able to properly execute the SPC that the statistical consultants were expecting. Next, there was also equipment maintenance oversight since the maintenance employee thought he solved the problem by moving the adjustment up, even though he was asked to make them lower. Initially, he did not tell the operators what happened, so there was miscommunication. And after careful and proper analysis, they found out that the threaded studs were so worn out that it was impossible to hold the lock nut in place.
Now we know what transpired. We created a fishbone diagram to identify the root cause of the problem of high rework and scrub syringes. The main problem for us was management oversight since they don't have a preventive measure in place, especially on the monitoring and maintenance of machines used in the process. A worn threaded stud on a machine used to adjust syringe length is causing the machine to drift off center and produce inconsistent syringe lengths. Now, moving on to identifying 3 alternative courses for the company, along with the pros and cons of implementing them. First is to develop a preventive maintenance program so they can regularly check the machines to ensure effectiveness. The pros of this includes increase the reliability of the machine's use, reduce wear and tear of machine, reduces delays and downtimes and process, thus stabilizing process capability. On the other hand, the cons are requires cost and resources, does not have real-time monitoring, possibility of overlooking underlying issues, and does not address the hassles of 100% inspection required in the second stage of production.
The next alternative is to invest in more accurate and reliable measurement tools that reduce human error with real-time monitoring and adjustments. Basically, a more technologically advanced SPC. So the pros include the operators will immediately know if there's something wrong and can make adjustments quickly, there's higher efficiency, and it reduces human error and enhances product quality and consistency. As for the cons, these include high initial investment for the measurement tools, especially if they are automated, and that operators should be trained properly with advanced measurement tools, which can be both time-consuming and costly.
And lastly, Midwest Pharmaceutical can deploy a quality control team to oversee the overall assembly line process of syringes. The pros includes provides an overall and comprehensive oversight of the production process of the syringes, quickly identifies and addresses the problems, continues a long-term improvement and improvement of quality. On the other hand, the cons are requires significant allocation of resources such as personnel, training, maintenance, and many more. Effectiveness and setting up meeting may take more time, and an increase in operational costs such as wages, equipment, training expenses, and etc.
To decide which alternative will be able to meet the needs of the company in terms of resolving the main problem, a decision matrix will be employed. The criteria are predetermined by this group according to the capability of the solution to resolve the problem with longevity and with minimized impact to the company. First, cost refers to how much the solution will require monetary support to execute. The higher the cost means the lower the score. Second, reliability refers to the capability of the solution to resolve the problem. The more it impacts the problem, the higher the score. Third, sustainability refers to how the solution will be able to withstand the test of time with minimal maintenance. The higher the score translates to the solution being able to last for longer periods. And lastly, time or effort needed refers to how much maintenance the solution would need before it could be executed and how much it needs to be maintained. The higher the score means the less time or effort needed. With that, we rank the criteria with reliability and sustainability as the top priority, having the higher weights, and cost having the lowest weight. Through our calculations, ACA2 garnered the highest weighted score. With that being said, we will be employing the second ACA2 challenge of the problem, and this is to invest in tools and our equipment that are reliable and be able to meet the needs of the company in terms of accurate reporting and be able to reduce human error.
Let's walk into our ACA journey where we follow PDCA cycle to keep things smooth. We start by setting clear goals and planning each step of the ACA implementation. As we move to action, we team up with our partners and make sure our team is ready to through targeted training. In the active phase, we adjust based on what we learn, backed by a study to refine our approach. Using control charts, we aim to improve how we operate, keeping an eye on our progress, and continuous monitoring guides us. Communication and collaboration are crucial, making sure everyone is on the same page. Approaching the end, we look deep into what's causing any issues with root cause analysis, paving the way with the lasting improvement, and each move, aligned with the PDCA cycle, boosts our confidence towards successfully finishing our ACA implementation. Moving forward, we anticipate and address several challenges in our ACA implementation. Challenges with maintenance. The introduction of new tools bring the need for regular maintenance to ensure sustained accuracy, adding a layer of complexity to our ongoing operations. Second is unforeseen expenses. Expenses tied to training, integration, and ongoing maintenance pose potential unforeseen financial impacts that need careful consideration. Third is dependency on technology. Our reliance on technology introduces the risk of technical glitches, malfunctions, or system failures that could disrupt our operations unexpectedly. Fourth is resistance to technological change. We recognize that some employees or stakeholders may resist the adoption of new measurement tools, potentially affecting the smooth implementation of the ACA. These challenges underscore the importance of our proactive approach and continuous monitoring as we navigate through ACA implementation journey. And that concludes our presentation. Again, we are Team Juran and we thank everyone for listening.